Welcome to the third lesson in Session 3 on exponential and logarithmic form. In the first two lessons, we focused on exponential functions and inverse functions. In the last lesson, we learned that an inverse of an exponential function is called a logarithmic function. This is important because logarithmic functions help us to solve problems when the variable is expressed as the exponent. The statement reads, the logarithm to the base b of a positive number y is defined as if y is equal to b to the x, then log base b of y equals x. Using this translation, it's important to remember that any logarithm can be expressed as an exponent, and any exponent can be expressed as a logarithm. In exponential form, you have y equals b to the x. Notice the placement of y, b, and x. In logarithmic form, we have log base b of y equals x. So the relationship that I like to point out is the base of both expressions is b. The base in exponential form acts as the base of the logarithm, which is b. And the x is expressed as an exponent in exponential form is equal to in logarithmic form. Here we're going to complete the following table. The left side we have exponential form, y equals b to the x power. And on the right side we have logarithmic form, log of base b of y equals x. So in the first one we have an entry in the exponential form side, 2 to the 5th is equal to 32. So as we translate that over to the right side into logarithmic form, it will read log base 2 of 32 is equal to 5. Notice in exponential form I had a base 2, in logarithmic form I have base 2. And then my logarithm is equal to the exponent. So my logarithm is equal to 5, which is the exponent on the left side column. Now going the other way, I have log base 5 of 5 equal to 1. So as we translate that over, that gives us 5 to the first equals 5. So what you want to notice here is that a logarithm where the base and the number are equivalent will always be equal to 1. Next we have 4 to the third is equal to 64. That's going to translate to log base 4 of 64 equal to 3. Here we have log of 100 is equal to 2. Notice I don't have a base in this expression. A logarithm of base 10 is referred to as the common log and is usually expressed without a base. So if you ever experience a logarithm that does not contain a base, we automatically default that base to a base 10. It's referred to again as the common log. So log of 100 equal to 2 translates to 10 to the second equal to 100. Here we have 3 to the third is equal to 27. That translates over to log base 3 of 27 equal to 3. And lastly, we have log base 3 of 1 over 81 equal to negative 4. If you have a logarithm that is equal to a negative number, that's going to indicate that we have a negative exponent. So this translates as 3 to the negative 4 power is equal to 1 over 81. Here we have a few more translations. In the first set of examples, we're going to translate the equations into exponential form. So log base 2 of 8 is equal to 3, translates into 2 to the third equal to 8. Log base 3 of 81 equal to 4 translates into 3 to the fourth equals 81. And log of 1000 equal to 3, again, there is no base there. We refer to that as the common log, and that translates into 10 to the third power is equal to 1000. In the last set of examples, we're going to translate equations from logarithmic exponential form into logarithmic form. So in the first one, we have 3 to the third is equal to 27, and that's going to translate to log base 3 of 27 equal to 3. 2 to the fourth power is equal to 16, and that translates to log base 2 of 16 equals 4. And finally, we have 5 to the third is equal to 125, and that's going to translate to log base 5 of 125 equal to 3. It's very important to be able to maneuver back and forth fairly seamlessly between exponential form and logarithmic form. Please feel free to email us if you have any questions. Good luck on the quiz.